Okay, we are recording. So today we are going to see one of the first encryption algorithm that got commercial success in the world. It is called DES, Data Encryption Standard. So it's one of the most widely used encryption algorithm. It was adopted by the NIST in 1977, so many years ago, as you will see. And it will work on block. We have two types of encryption algorithm, those that work on stream and those that work on block. So when we are going to encrypt a string or a file, we will take block of 64 bits, encrypt them, then the next block of 64 bits, encrypt them, and we will repeat that until the end of the message that we want to encrypt. So the key is 64 bits, as they say here, but of the 64 bits, we will not use all of them. We will just use 56 bits. So you will see that some people will say that DES have 64 bits, other people will say that DES have 56 bits, because of the 64, we lose 8 bits that will be used for parity check, and or not used at all. It's why some other people will just say that we have 56 bits. Effectively, it's 56 bits. We will see that the algorithm uses 16 rounds. So we'll do the same step 16 times before we get the ciphertext. And from the key, which will be 64 bits or 56 bits, we will generate subkeys, intermediate subkeys, and we will generate 16 subkeys. And we will use one of the subkey for each iteration, because there are 16 iterations. We will generate a subkey for each iteration. So it's a symmetric encryption algorithm, which means that the key that we are going to use to encrypt and to decrypt is the same one. So the sender and the receiver have to agree on a common key. So here we have the encryption algorithm. You have two inputs, the plain text and the key. It will produce a ciphertext. This ciphertext, I should not worry about somebody getting a copy, because it's supposed that the person will not be able to go back to the plain text unless this person is the destination that I want. And here we have the decryption algorithm at the level of the recipient. So it has two inputs, the ciphertext, the same key. That's why it's called a symmetric algorithm. And it will produce the plain text. And the plain text have to be a copy of the original plain text, of course, you know. So this is the algorithm. So I'm going to explain this part first. The generation of the 16 subkey. So you will take the key, which is 64 bits, and you will apply a first operation, which is called PC1. PC for permuted choice 1. And PC1 will do two things. It will reduce the number of bits from 64 to 56, and it will change the position of the bit that it will keep. The new key, we will call it K+. So K+ is 56 bits. So we will remove the bit that we don't use. As I was telling you, it's 64 bits, but really there is 56 bits. So then we will generate the subkey. We need 16 subkeys. So from key 1 to key 16. So with K+, we'll make a circular rotation of K+, and after this circular rotation, one position to the left, we will apply a second table, which is called PC2. And this will give us the first subkey. So to get the second subkey, look at the path. I make a first circular rotation, then I make a second circular rotation. And from the result, I also apply PC2. the permuted choice 2 table, and I will get the second subkey. So you get all the 16 subkey, and the subkey are 48-bit long. Then you will take the plain text, which is a block of 64 bits, and you will apply a first table, which we will call IP for initial permutation. This first table will just shuffle the bits, but it will not reduce the bit in size, or it will not add bits. Sometimes operation add bits, sometimes operation remove bit, and sometimes operation just shuffle the bits. So the initial permutation will just shuffle the bits. So the input will be 64 bit of plain text, and the output of initial permutation will be also 64 bits. Then we will have 16 round, 16 iteration. So we will take this input with the key one, and we will have an output which is 64 bits. Then the same operation, this block is the same black box, no? It will have 2 inputs, 64 bits, and a subkey, which will be the second subkey, and it will generate 64 bits in output. So we will do that 16 times. So here, as you can see, the input is 64 bits. We also have as input the key K16, and it will have an output which is 64 bits. Before getting the ciphertext, we will swap the most significant 32 bits with the least significant 32 bits. We will just swap them. And there is this initial permutation, since it's a bijection, we can compute the inverse of this bijection and create what we will call the initial permutation inverse, the inverse of the initial permutation. And we will apply this inverse at the end, and here we will get the ciphertext. So I'm going to go through all those steps very slowly with details so you know this algorithm very well. This is the only algorithm that I'm going to explain in this class. There are a lot of algorithms, like for example, advanced encryption standard is one, IDE is another algorithm, blowfish, twofish are other algorithms. So there are a lot of algorithms, but I'm just going to explain one of the algorithm, which is data encryption standard, which is DES, the one that I just started with. So let's start with what we will be doing. So the key here will have at the beginning 64 bits. So it will be 8 bytes. So this is 1 byte. There is a second, a third, a fourth, up to the last byte. So a total of 8 bytes. If we have 8 bytes, we have 64 bits, as you can see, no? So the bits here, the number is 1 to 8, and the last byte, the number will be 57 to 64. So this bit, the least significant of each byte, will not be part of the key. So for each byte, I'm going to lose 1 bit. So since we have 8 bytes, I'm going to lose 8 bits. This is the way to show that at the end, even if the key is 64 bits, I will be using of the 64 only 56 bits. So for each byte, we will use 1 bit, no? We can use it also as a parity bit. So some implementation will use it as a parity bit. But today, storage is very safe. We don't need parity bit anymore because it's very unlikely that the information would get corrupt, no? So that was good at the time that they did this, which was 1977. The storage was not as good as they are today. But today, the parity bit is not important anymore. So most of the implementation of DES just drop this bit without checking the parity. So there is a first table that we will use when we generate the 16 subkey. And this table is called PC1, permuted choice 1. So let's understand how it works. Look at it. Here I have a figure of what will happen. So the input of PC1 will be a data of 64 bits. And the output, oh, you don't see the lower part, so sad. The output, let me see if I can do something for that. How can I make this disappear? Do you know if there is a way for me to make this disappear? I did it for one moment. Oh, yeah. Okay. So from 64 bits, we'll go to 56 bits using this table. So this table say that the first bit of the result will be bit 57 of the input. So if you look, this is the input and this is the output. So I go to bit 57, and if you follow this line takes you to bit 1. So bit 57 of the input will be bit 1 of the output. Bit 94 of the input will be the second bit of the output. So bit 94 is there. If you follow this line, it will take you to the second bit. Bit 41 of the input will be the third bit of the output. So if you look here, bit 41, and I follow this purple arrow, it takes me to bit 3. So if I look at the last 3 bits of the result, the bit that is in position 54 will be bit 20. So bit 20, let me go to bit 20 here, which is this one. If I follow it, it will take me to position 54. The bit that is next to the last will be bit 12 of the input. So here, if I take this bit, it is in red, and I follow the arrow or the line, it will take me to these bits. And the last bit in the result or in the output will be bit 4 of the input. So if I take bit 4 here and I follow this black line, it will take me here. So you understand how this PC1 works? Okay, so as you can see, look at bit 8 don't have an arrow that go out, which means that bit 8 is lost. Bit 16 also, bit 24, bit 32, which is the least significant bit of each byte is lost. So this is a byte. The least significant bit will be 8. This is another byte. The least significant bit will be 16. It is lost. So as you can see in the table PC1, we don't have 8. We don't have 16. We don't have 24. We don't have 32. Okay, because we lose those bits. The other one are shuffled, no, as you can see, and we lose 8 bits. So this result, we will call it K plus. And K plus, the length of K plus will be 56 bits. So here is an example. Let's say that the key is DA2C up to 94. So if you count them, you will see that this is a 64-bit key. So I want to compute key plus, which means I want to apply to this key, I want to apply PC1. So to make it easy, I put the key here in binary. So let's see, D4 1101 is D. So DA, sorry, and A is 1010. Then we have 2C, 0010 is 2, and C is 1100, okay? If I want to verify the last 2 digits, we have 94. 9 is 1001 in binary, and 4 is 0100. So this is the key in binary. So let's see what PC1 say. It say that in the result, the first bit will be bit 57. So look at in blue here. 01 means that this is bit 1, bit 2. So you see, I put, for example, this will be bit 57. So I just put numbers to know which bit is which one. So I need bit 57. Bit 57 is this one. You see it? 57 is this one. So this one will be the first in the result in K plus. Then we need bit 49. So 49 is this bit in the input. It will be the second bit in the output. Then we have, as third bit, we have bit 41. 41 is this column. So the input bit is 1. We will have 1 as the third bit. Let me do the last 3 bit, this 101. So this one should be bit 20. So let me find bit 20. Bit 20 is this bit. So it's a 1. So this one will be this one. Then the next to the last, I need bit 12. So I look for bit 12. Here is 12. Bit 12 is a 0. So this 0 will come here. Then the last bit will be bit 4 from the input. So from the input, bit 04 is a 1. So this one will come here. So this will be K plus. And K plus, as you can see, is F1, 5, D, 6, 6. Okay, we will write it at one point in hexadecimal, no? So this is the first thing that we have to do to compute K plus. Then we need to apply rotations, left rotation. So let me show you again the first slides. We just applied PC1. So we went from 64 bits to 56 bits. Now we need to make a left rotation. So, and then apply PC2 to get the first sub key, K1. So let's see. Look, here you have, for the first iteration, they say you have to apply 1 rotation. For the second iteration, which means to compute K1, the subkey K1, you need 1 rotation. To compute the key K2, you need 1 rotation. To compute the subkey K3, you need 2 rotations. So if you look at this column, you need either 1 rotation or 2 rotation. So for example, to compute the key K14, you need 2 rotation. To compute the key K10, you need 2 rotation. So from K plus, we are going to compute the first subkey. So what we are going to do is to divide this 56 bits into half. So the left part will be called C sub 0, and the right part will be called D sub 0. So each of them will have 28 bits, no? Because 56 divided by 2 give you 28. So C0 will be the most significant 28 bits, and D0 will be the least significant 28 bits. So what we are going to do here, they say to get K1, we need to make 1 rotation to the left. So we are going to take C0, and we are going to make with C0 1 rotation to the left. And we are going to take D0, and we are going to do with D0 1 rotation to the left. And this will give us C1 and D1. Then to compute C2 and D2, here the 2 say you need to do also 1 rotation to the left. So I'm going to take C1 and make 1 rotation to the left. And I'm going to take D1 and make 1 rotation to the left. Now to go from D2 to D3, you need to make 2 rotations to the left. So I'm going to take C2 and make 2 rotations to the left to get C3. And I'm going to take D2, make 2 rotations to the left to get D3. And I'm going to go up to C16 and D16. This is what they say here that you have to do. So let's see an example. So we already know how to go from K to K plus using PC1, the permuted choice 1 table that we saw. So then we divide K plus into block of 28 bits. So the first 28 bits will go up to up to here. So it will include 1110. And the other 28-bit, the least significant 28-bit, start here and go up to that. So the most significant 28 bits, I will call them C0. And the least significant 28 bits, I will call them D0. So how do I go from C0 to C1? I make one rotation to the left. So if you make one rotation, do you know what is a rotation? So this one, you run it here. So you run each bit to the left. And the most significant bits come to be the least significant bit. So this one is here. Let me show not over 28 bit what is a rotation left. Over less bits, I will explain you what it is, just in case that you don't know it. So let me open Paint. So let's say that I have 4 bits, and I want to explain you what is a rotation to the left. So this bit will go here. This bit will go here. This bit will go here, and the most significant bit will go here. This is called one rotation to the left. So if I take 1, 0, 1, 1, and I make one rotation to the left, let me put rotation one time, rotation left. Let me put rotation left one time. Will be what? What will be the result? Exactly, 0, 1, 1, 1. If I make rotation left 2 positions this time of the same number, what will be the result? 1, 1, 1, 0, isn't it? Because you apply 2 times a rotation to the left. So you apply this 2 times. Okay? Is it okay for everybody? So let me go back. So look, we take C0 and we make one rotation to the left and we get C1. How do we go from C1 to C2? We take C1 and we make one rotation to the left. So if you look this number, if I remove this one and I put this one at the end, I will get C2. Now, according to the table that we have, how do we go from C2 to C3? Making 2 rotations to the left. So if I suppress these 2, 1, and I put them at the end, you will get this number. So sometimes it's 1 rotation to the left, sometimes it's 2 rotations to the left. So remember, to get C1 and D1, it was 1 rotation to the left, from C0 and D0. To get C2 and D2, it was 1 rotation to the left. But to get, for example, C3 and D3, it was 2 rotations. Then again 2, then again 2, 2, 2, 2, then 1 to get C9 from C8 and D8, 1 rotation to the left. So sometimes it's 2 rotations, sometimes it's 1 rotation. So for example, look, from here to here, we can see how many rotations to the left I have done. 2, no? I take this 0, 1 and put them at the end. So you do that for I that vary from 1 to 16. And you will get up to C16 and D16. Now, how we compute? We need 16 subkey. So from C1 and D1, I need to compute K1. And from C2, D2, I need to compute K2. And from C16, D16, I need to compute K16. So for that, we will use another PC2, another table, which is called PC2, permuted choice 2 table. So here is the permuted choice 2 table. There is a graphic here that will show you what it will do. So look, we will do the concatenation of CE and DE. So remember, CE is 28 bits and DE is 28 bits. So the concatenation will be 56 bits. And so it will be the input of PC2. And we will apply PC2. And PC2 will reduce the 56 bits into 48 bits. So as you can see, how do we go? Bit 14 of the input will be the first bit of the output. So if you look here, bit 14 is this red one. So if I follow the arrow, it takes me to bit 1. Bit 17 of the output will be the second bit of the bit 17 of the input will be the second bit of the output. So if I go here, 17 is the green one. If I follow it, it's the second. Bit 11 of the input will be the third bit of the output. So if I look for bit 11 and I follow the arrow, it's taking me to the third bits. So you will use this PC2. Okay, notice that we lose some bit. Of course, if we go from 56 bits to 48, we did lose 8 bits. So the bit that are lost is bit 9. So if you look here, bit 9 is not used. Another that is not used is bit 18. Bit 22 also is not used. Okay, so we will lose in this permutation some bits. And we will go from 56 bits to 48 bits. So if I come back to the first slide, look, you have an input that is 56 bits. You apply PC2 and the output is 48 bits. So we will get K1. Then you will get K2 up to K16, the 16 sub keys that you need to apply the data encryption algorithm. So I already explained you how we generate the keys. Let's see an example. For example, let's see how we generate K1. So let's say that you already generated C1, D1, C2, D2 up to C16, D16. You want to go from C1, D1 to K1. So here I put the information of C1, D1. First you concatenate C1 and D1. So 28 bits and 28 bits will give me 56 bits. Then I just put numbers, no? So this is bit 1, bit 2, bit 3, up to bit 56. So I know that, for example, this bit is bit 53. Then we apply this table. So I need bit 14 as the result here. So where is bit 14? It's this one. Bit 14 is in the input is this 0. So this 0 will go here. Then I need bit 17. So bit 17 is this one in the input. So this one will go a second bit. Then I need bit 11. So where is bit 11? Is this one. So this one will be the third bit. Let me do the last 2 bits. I need bit 29. So bit 29 is this one, is this 0. So this 0 will go here as the bit next to the last. And the last bit will be bit 32. So I need bit 32, it's a 0. So this 0 will go here. So this will give me the first sub key. And I apply that 16 times and I will get all the sub keys. So there is an example here how to compute the second sub key. So of course you have C2, D2, you concatenate them, then you apply PC2 and you will get the sub key, key 2. So here are the results. We will get the 16 sub keys. Okay? And we need 1 sub key for each iteration. Remember that we are going to do 16 iterations. So before we continue, let me go back to the slides here. So we already generate key 1, key 2 up to key 16. So we did this part. Now we are going to take the plain text, the one that we want to encrypt. And we are going to pass the plain text through a table that is called IP, initial permutation. So the input will be 64-bit and the output will be 64-bit. Initial permutation will just shuffle the bits, just move them around. but it will keep the number of bits and the value of the bits. So if I go back here, look, this is initial permutation. So it will take 64 bits as an input, and the output will be 64 bits. So if you look, 1 is 2 is there, 2 is there, 3 is there. All the number from 1 to 64 will be there, because this is a bijection. So there is a way that you can compute the inverse of the initial permutation. So the initial permutation will do that. It will take 64 bits as an input and generate 64 bits as an output. There is no loss, there is no creation, just shuffling the bits. So as you can see, bit 58 of the input, which is this blue, if I follow this arrow, will be the first bit of the output. Bit 15 of the input, which is this bit, will be the second bit of the output, as you can see. And if I look at the last bit, which is bit of the output, which is this bit, it will be bit 7 of the input. So if I take bit 7 of the input and I follow this line, it takes me to bit 64. So this is the way that we are going to apply the initial permutation. Then, after the initial permutation, we enter in the repetition that we will do 16 times. So let me go back to the original slides. After the initial permutation, you go the first round, then the second round, up to round 16. So each round will have 2 inputs. The output of the previous round, so if you look at round 2, one of the input is the output of the previous round, and a sub key. So in round 1, we will use sub key 1. In round 2, we will use sub key 2. In round 16, we will use sub key 16. So 2 input, one is 64 bits, the other one is 48 bits, and 1 output, which is 64 bits. So let me go back to the slides where we were. Okay, so let's see our example. Let's say that the clear text message or the plain text message is this one. So this is 64-bit long. So I wrote it here in binary to make it easier. And in blue, we have the numeration. So for example, this bit is bit 33. This bit is bit 40, as you can see. So we are going to apply the initial permutation to get what we will call IP. So how we got IP? The first bit of IP, which is this 0, will be bit 58 of the plain text message. So bit 58 is this one, it's a 0. So this 0 will come here. The second bit of IP will be bit 15 of the plain text. So let me find bit 15. Bit 15 is this one, it's a 0. So this 0 will be the second bit. Let's do the third bit. Bit 42, where is bit 42 is this one, it's a 0. So this 0 will be the third bit. Bit 34 will be the fourth bit. So bit 34 is the 0. It will be the fourth bit. Then bit 26 will be the fifth bit in the result. Let me take bit 26. Bit 26 is the 1. So this one will be the fifth bit in the result. So I keep going and I will compute what is called IP. And this IP will be the input of the first round with the sub key K1. So IP is 64 bits long and the sub key K1 is 48 bit long. And there is a black box that we are going to explain is what each round will do. So here I have information of each round. So in the upper part, you have the result of the previous round, which is a data of 64 bits. So 32 plus 32 is 64 bits. Here you have a key. So in round I, we use the sub key Ki sub I. So it's 48 bits. So 64 bits of input, 48 bits of input, and we have an output that go to the next round, which is 64 bits. So as you can see, look at what we do. The 64 bits, we will divide it in two parts. The most significant 32 bits, we are going to call them left, sub I minus 1. This is iteration I. The least significant 32 bits, we are going to call them right I sub I minus 1. So as you can see, we take these 32 bits, look at them, we take these 32 bits, and they will go to the next level as the most significant bits. So if you look, the output, which is left I, is just a copy of right I minus 1. So right I minus 1, which is 32 bits, I just copy them as the output. Now, to compute the least significant 32 bits, it's a little more complex. So we take the 32 bits, the least significant 32 bits, and we are going to XOR them with another 32 bits. And this result will be the right part of the output, the 32 bits of the right part. So here we have 32 bits. And how we compute these 32 bits? So there is a function f, and this function f depends on two entries. So one entry is r sub I minus 1, which is the 32 bit, the right 32 bits of the previous round, and the key of the round, which is 48 bits. So this function will do something. It will do 4 operations, as we will see, and will generate a result which is 32 bits long. We will XOR this result with the left 32 bits of the previous round to get the right 32 bits that are going to enter the next round. So I need to explain what is this f. So this f will do 4 operations, as we will see. So there is, the first step will be an extension. So we are going to extend this 32 bit to 48 bits. The second step will be a XOR. We are going to do an XOR of the new 48 bit with the key of the iteration. Then we are going to use X boxes as a third step. And then finally, we have a permutation. So we have 4 steps here in the f function. I'm going to explain them. So function f of this. Okay, so we need 4 steps here. I explained the first 3 steps. So the first one is to take the rightmost 32 bits of the previous iteration and to convert them to 48 bits. So if you go from 32 bits to 48 bits, you are going to duplicate some bits. So we will see that this operation, which is called extension or expansion table, I will say extension or expansion table, is going to duplicate some bits. So for example, if you look, we can see that bit 1 is repeated. So we'll have bit 1, which is the input, 2 times in the output. So if you look bit 1, it will be copied at bit 2, and it will also be copied at bit 48. So this is bit 2, and this is bit 48. If you look, bit 4 also appear 2 times. 1 time here, 1 time here in the result. So look at bit 4. There is 2 lines that leave bit 4. It's copied here, and it is copied here. Another bit that will be repeated is bit 5. So you see bit 5 is here and is here. Another bit is bit 8. It is here and it is here. Another bit is bin 9, it is here and it is here. So all those bits will be duplicated. So I can expand from 32 bits to 48 bits. So that will be the first step. I say that there are 4 steps. So the first step will be an expansion. You will expand the rightmost 32 bits of the previous iteration to get something that is 48 bit long. When it's 48 bits long, you are going to make an XOR of the key of the iteration with the result of the first operation. Remember, the result of the first operation is to apply the extension table. So 48 bits XOR 48 bits will give you a result that is 48 bits long. Then the third step is explained here. We have 48 bits. We are going to divide these 48 bits in each block of 6 bits. And for each block of 6 bits, we are going to apply a S table. So we have 8 S tables. And I'm going to explain you how we apply the S table. So the S table have 4 rows. Each S table have 4 rows and 16 columns. So we need a way to select a row and a way to select a column. And the intersection of a row and a column will give us one element. And we will replace a block of 6 bits with a block of 4 bits, as we will see. So let me go there to explain you a little more. So look, when you have done the XOR, which is the second operation, the result is 48 bits. So you create 8 blocks of 6 bits. So B1 have 6 bits, B2 have 6 bits, up to B8 that have 6 bits. Then for the first block of 6 bits, you apply the first S box. So box S1. This result will be 4 bits. Then for the second block, which is 6 bits long, you apply the second S box, which is S2. You will get 4 bits. So you get 4 bits here, 4 bits here, 4 bits here, up to 4 bits here. So 4 times 8 is 32. So the result will be 32 bits. So how do you select in the S table the row and the column? So look, each block here have 6 bits. So you will take the first bit and bit 6 together, and it will be a number of 2 bits. A number of 2 bits is something between 0 and 3. It will give you a row. Remember that we have 4 rows. If we have 4 rows, we need a number between 0 and 3. How do you select the column? We have 16 columns. So you will take the bits that are in the center, from bit 2 to bit 5. We have 1, 2, 3, 4 bits. If we have 4 bits, we can go from 0 to 15. So from 0 to 15, we will select a column. So remember, the first and 6 bits, the 2 ones that are in the beginning and the end, will give me the row. And the ones that are in the center will give me the column. I will make the intersection of a row and a column, and there will be a 4-bit number. This 4-bit number is the one that I'm going to use to replace each application of S to a block. So for example, when I apply to B1 the box S1, I will get 4 bits. Here I will get 4 bits, and I was telling you that the result will be 4 times 8, which is 32 bits. So let's see that. This is the S box S1. As you can see, 1, 2, 3, 4 rows and 16 columns. And if you look inside, all the numbers are between 0 and 15. If a number is between 0 and 15 and I represent it in binary, I need 4 bits. It's why I was telling you we will go from 6-bit to 4-bit because we need 6-bit to select one element in an X box. So we have S1 for the first block, S2 for the second block, S3, S4, S5, S6, S7, and S8. You remember that we have 8 blocks. So let me go back. S1 is the one that I just showed you. We'll apply it to block 1. S2 is the one that I just showed you. We'll apply it to block 2. Up to S8, we will apply it to block 8. So let's see an example. Let's say that block 1 is, remember block 1 is 6 bits. And when I apply S1, it has to be reduced in 4 bits. So how do I select the row? I take the first bit and the last bit. So 0, 1. Okay? Bit 1 and bit 6. 0, 1 is 1. So I need to select row 1. So this row. Now I need a column. How do I get the column? I take the bits that are inside, the center bits. So inside, between bit 2 and bit 5, I have 1, 1, 0, 0. 1, 1, 0, 0 is what? Is 12. So I need column 12. So I'm going to do the intersection between row 1 and column 12. I get this 9. And 9 in binary is 1, 0, 0, 1, which means this first block of 6 bits is going to be replaced by this block of 4 bits. Let's see a second example. Let's say that this one, B1, is this block of 6 bits. And I need to know the 4 bit that will replace these 6 bits. So I take the first bit on bit 6. So it's 1, 1. As you can see here, bit 1 on bit 6 will be 1, 1. 1, 1 give me 3. So I need to select row 3. Now, how do I select the column? I select bit 2, bit 3, bit 4, and bit 5. So it's 1, 0, 0, 0. 1, 0, 0, 0 is 8. So I'm going to take column 8. So row 3 with column 8 give me 5. And 5 in binary over 4 bits is 0, 1, 0, 1, which means that this 6 bit will be replaced by these 4 bits. So let me go back. Now you should have understand B1 is 6 bits, and I apply S1, I get 4 bits. B2 is 6 bits, I apply S2, I will get 4 bits. B3 is 6 bits, I apply S3, and I will get 4 bits. Up to bit B8 is 6 bits, I apply S8, and I will get 4 bits. So the result will be, since each block here is 4 bits, 4 times 8 is 32 bits. The result is 32 bits, okay? Okay, now that you have 32 bits, you are going to use P. This is the 4th step of the function f. Remember, function f have 4 steps. First step, I use the expansion table. Second step, I make a XOR between the result of the expansion table and the key of the iteration, the subkey of the iteration. Third step, I use the Xbox. So here we can see the first step. I use the extension table. Second step, I do a XOR. Third step, I use the Xbox. And fourth step, I use P, which is this table, a permutation. So as you can see, it will take an entry of 32 bits and will give me an output of 32 bits. So this is when we apply F. So look at F, have 2 inputs. The rightmost bit, the 32 rightmost bit of the previous iteration, which is R sub I minus 1, the key of the iteration, which are 48 bits. And first, we apply the extension table. Then we do a XOR with the key. Then we apply the SS box. And then we apply P, which is this iteration. And after applying P, the result will be 32 bits. So these 32 bits, I'm going to XOR them with the 32 leftmost bit of the previous iteration, and there will be the input of the next iteration. There will be my output and the input of the next iteration. There will be the output of iteration I, and there will be the input of iteration I plus 1. Okay? So another way to see that is this way. I take the 32 rightmost bits of the previous iteration, which is R sub I minus 1. I expand them with the expansion table. They become 48 bits. I take the key of the iteration, which is K sub I. I XOR them. The result is over 15.6 bits. I break the 15.6 bit in 8 blocks of 6 bits. So this will be block 1, block 2, block 3, up to block 8. On block 1, I have to go from 6 bits to 4 bits using the S1 table. So in the S1 table, to know what is the row, I take the first bit and the last bit. And to know what is the column, I take these 4 bits. Okay, and it will give me the column. And this will give me 4 bits. Then I apply the P table, the permutation, and it will give me the output of function f. So this, let me go back to the first slide. I explain what is inside the black box. So you will have an output which is 64 bits. You apply it in a second round, third round, fourth round, up to round 16. And there is 2 final operations before we get the ciphertext. So we will swap the most significant 32 bits with the least significant 32 bits. So here we will swap 32 bits with 32 bits. And then this initial permutation, we will take the inverse and apply it as a last step. So let me go back to the slides where we were to show that. So here, look, I'm explaining in this slide how you will compute, for example, as input of iteration 1, you have 64 bits. On these 64 bits, you break them in 32 bits and 32 bits. The leftmost 32 bits and the rightmost 32 bits. So the L sub 0 and R sub 0 are input of round 1. Another thing that is input of round 1 is K1. And the output of round 1 are going to be left 1 and right 1. So we need to compute left 1 and right 1. So left 1 will just be R sub 0. So this is R sub 0. So this R sub 0, I just copy it as left 1. So left 1 is very easy to get. It's just a copy of R0. Now I need R1. So I need first to apply the f function. 4 steps to apply the f function. So let's see the steps. First, I take R0, which is this guy, and I apply the extension table. So it will bring it from 32 bits to 48. So look, by applying the extension table, I get this result. You can apply it. Here is the extension table, no? So for example, bit 32 of R0, bit 32 will be this one, will be the first bit here. Then bit 1. Bit 1 of R0 is D0, will be the second bit here. So I apply the E table, the extension table, and I get that. Then you need to do an XOR, as you can see, between this result and the key of the iteration. So you do an XOR between this 48-bit number and this 48-bit number, and you get this result. Now I put 2 colors because I need to break them in group of 6 bits. So the first 6 bits will be called B1. Then the other 6 bits, B2, B3, B4, B5, B6 is the 6 bit that I put them, B7, I put them, and B8. For B1, you apply the S1 table. And when you apply the S1 table, it will give you this 4 bit. For B2, you apply the S2 table. It will give you this 4 bit. Blah, 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 blah. Up for B8, you apply the S8 table. It will give you this 4 bit. Then over this binary number, which is 32 bits, you apply the P table, the permutation table that we saw, this one. And you will get this result. So this result is this. You will XOR it with L0. So you XOR this with L0 and you will get that. So that will be the rightmost bit of the output, the 32 rightmost bit of the output. And this will be the 32 leftmost bit of the output. And this output is going to enter in the next iteration, the next, you apply that 60 times. So you keep doing that 60 times, and at the end, so this is round 2, the result of round 2. This is the result of 115 if you want to verify them, the result of 116 because you do it 16 times. And then you need to swap after round 16, you will have left 16 and right 16. You will swap them. And after swapping them, you need to apply the initial permutation, the inverse of the initial permutation. So this is the inverse of the initial permutation, and you just apply it. So here there is a drawing that shows you that, for example, you take bit 14 from the input, and it will be the first bit of the output. So if I take bit 14 and I follow the line here, it's taking me to the first bit. So this is the inverse of the initial permutation. So look, after iteration 16, you have the left part and the right part. You need to swap them. So I'm going to put the right part first. So this one is this one. On the left part, I'm going to put it second. Then I apply the inverse of the initial permutation. So it says that this is the result of swapping. I need first bit 40. So bit 40 is this one. So I will take this one and put it in the ciphertext here. Then I need bit 8. Bit 8 is this 0. I will take this 0 and put it here. So this, you apply the inverse of the initial permutation and you get the ciphertext. So look at, if the key was this, the plain text was this, the ciphertext will be this. Okay, did you understand how we apply that? We do have some exercises to clarify how it's worked. But do you have any doubt? Here you have a summary of all the operation. So that was the key that we use on the plain text. So first, we compute K plus using permuted choice 1, PC1, the table that we saw. On this, the result will be that. So we will go from 64 bits in the key to 56 bits. Then we break that in C0, D0. From here to here, it's a rotation left, one rotation left. From here to here, it's one rotation left. From here to here, it's two rotation left. From here to here, it's two rotation left. So remember, sometimes it's one rotation left, sometimes it's two rotation left. To generate all the sub key. So for example, the sub key K1 is the concatenation of C1 and D1. And the sub key K16 is the concatenation of C16 and D16. Okay? Oh, it's not the concatenation. There is another transformation. There is PC2. So we do concatenate them and then apply PC2. Okay? So we'll concatenate them and apply PC2. That was to generate the 16 sub key. Then on the other side, where we have 16 iteration. So the first thing, you apply IP, the initial permutation. Then you divide in left sub 0 and right sub 0. And you apply this black box that have the F function 16 times. So after the first iteration, you get L1, R1. After the second iteration, you get L2, R2. And after the last iteration, which is iteration 16, you get L16 and R16. Then you need to swap L16 and R16. This is what we are doing here. And finally apply the inverse of the initial permutation to get the result here. Okay, we do have some desk calculator online. So if you want, for example, to verify that if this is the plain text and this is the key, the ciphertext have to be this one, no? We can verify it. So let me, for example, go to one of these calculators. I'm going to use this one just to show you, because you will have exercises where you will have to do it. And last time, Firefox was not working either. So let me put Chrome. Okay, so this is a desk calculator. So here you are going to put the plain text. So let me copy the plain text from our exercise to verify that everything is okay. So the plain text is this one, which is 64-bit long. So let me copy it here. And the key is this one. And the ciphertext must be this one, no? So in the space of the key, here they say enter the clear text, enter the key. So I'm going to put the key, and there is a button that I have to hit. I select the encryption algorithm that I want, and I click here, encrypt, and this is the ciphertext. So we are going to compare it with what we have. So here we have it, 80B9, 80B9, 9B76, 9B76, up to the end, okay? So this is a very important algorithm, and it was done many years ago in 1977. And in 1977, the computer that we have at this time were not very powerful. And if you launch a brute force attack, how many possible keys you have for this? If you try all the keys, how many possible keys we will have? So how many bits have the key? It will be 2 to the power of the number of bits of the key. The key have, remember, it has 64, but of the 64, we only use 56. So it will be 2 to the power of 56. So 2 to the power of 56 for possible keys. If I launch a brute force attack in 1977 in a computer, in very good computer, it will take years, maybe more than 300 years, 500 years at this time. So of course, that was a very safe algorithm at this time. Now we are in 2022. The power of computing is much higher. So a normal computer takes some hours to break DES. So DES is not a secure algorithm anymore because the key is too small for the computer of today. We need keys that are longer. Since DES is a very good algorithm, they make some variant of DES with a longer key. So we are going to talk about those variants. So those variants are called triple DES. And we can use triple DES with 2 keys or 3 keys, as we will see. So here I'm going to talk about triple DES with 2 keys. So if I use 2 keys of 64 bits, 64 times 2, the key K will have 128 bits. But remember that really it's only 56 bits. So the effective key will be 56 times 2. And 56 times 2 is 112. So the effective key will be 112 bits. So look at what we are going to see. We need a key of 128 bits. So we are going to break this key in 2 sub-keys. The most significant 64 bits and the least significant 64 bits. So K1 will be 64 bits and K2 will be 64 bits. So what is triple DES with 2 keys? We have 2 keys, K1 and K2. So we will take the plain text and we will encrypt it with DES using this key, which is 64 bits. We will take the result and we will decrypt it with DES using this key. And we will take the result and we will encrypt it again with this key. And this will give us a result of 64 bits. That will be the result of encrypting this plain text with triple DES with 2 keys. So here there is something that is a little more graphic. So let's see. You enter a key, which is 128 bits, but you can separate it in 2 sub-keys, 64 more significant bits and 64 least significant bits. So here it's an encryption block of DES. So you have the plain text, and you take the 64 more significant bit to encrypt. Then the result, which is 64, you use the decryption algorithm of DES with the second key, which is 64 bits. And it will give you another 64 bits. And then you encrypt again with key 1. And this will be a new encryption algorithm that they use. When you go to an ATM machine, most of the ATM machine will use triple DES with 2 keys or with 3 keys. So we still use DES through triple DES. It's called triple DES because, as you can see, we apply DES 3 times. We encrypt with DES, we decrypt with DES, and we encrypt. And it's called triple DES with 2 keys because the key, which is 128 bits, is at the end 2 keys of 64 bits. So let's say that I have a ciphertext. How do I decrypt the ciphertext to come back to the plain text according to this drawing? What will be the first operation that I have to do? So look at, I move following this arrow. So if I am here and I want to come back to the plain text. So I need to move backward. If I move backward, what will be the first operation that I need to do? With the
You have to decrypt is the first step.
So the first operation that I have to do is to decrypt with K1. Then this result, to cancel the decryption here, I will have to encrypt it with K2. Then the result, to cancel the operation of the encryption here, I will have to decrypt it with K1. So you look, when I'm going to decrypt the ciphertext, I will do first decryption, then encryption, then decryption. Here, look at what we do. We do first encryption, then decryption, then encryption. So if you look at the decryption algorithm, look at it. We do first decryption with K1, then encryption with K2, this is what we say, and then decryption with K1. So applying it twice, we'll come back to the plain text. And I can, if you want, we can see it here. We can put that in, I can start Paint and see that if I apply them twice, I will come back to the plain text. So let me do that. So here we have please remember that we are in class now. Okay, so I need you to follow with me and not do something else. Okay, so encryption of P is encryption of K1, as you can see here, then decryption with K2, then encryption with K1. This is the way that we are going to encrypt. So this is the way that we are going to decrypt. So I'm going to put, this will be C. I'm going to put C here to see if we come back to the plain text. So let's see. We have decryption of K1 here. Then we have encryption of K2 here. Then we have decryption of K1 here. Then we have the ciphertext. So the ciphertext is, I'm going to write it here. It's encryption of K1, decryption of K2, and encryption of K1. So 1, 2, 3, 4, 5, 6 parentheses. So what can we do here in this expression to simplify this expression? So if you look here, we have some result here that we first encrypt with K1, then we decrypt with K1. What will happen if I have some result, some value that I encrypt with K1 and decrypt with K1? I will get what at the end? I will end the same result. It will be identity. If you encrypt and then decrypt, you come back. So I can just remove these two and say that this will be, let me put it in black. This will be decrypt of K1, encrypt of K2. So I just remove that. So then we have decrypt of K2, encrypt of K1 of the plain text. I should have put here the plain text, I forgot. So we have that. Now what can we do to simplify this expression? So if you look here, we have, first we have a result. We first decrypt it with K2, then encrypt it with K1, K2. What will happen? The same result. So this will be decrypt of K1. So this will disappear. Encrypt of K1 of the plain text. And of course, here, I will have the plain text. I will encrypt it with K1 and decrypt it with K1. I will finish with what? With the plain text. So applying twice, applying the encryption algorithm and then the decryption algorithm, come back to the plain text. This is what I just showed here, no? So here they tell you why don't you do an exercise? So for example, they tell you, you have the following key. This is the key on the following plain text. So encrypt this using triple dash with 2 keys and show that the answer will be that. So since we have an online calculator, let's do it. Let me open Word and let's do it. So let me put the key on the plain text. Let me copy them. Here we have the key and we have the plain text. Okay, so let me copy this one also, so we know how to compute the ciphertext. So we have to apply this formula to compute the ciphertext. So what will be the first step to do that? I need to determine what? I need to determine what is key 1 and what is key 2, no? Because remember, this key, which is 128 bits, is the concatenation of 2 keys. So what will be key 1? Key 1 will be the most significant part. So 1, 2, 3, 4, 5, 6, 7, 8 bytes. So this one will be key 2, isn't it? So we have key 1 and key 2. So I need to take the plain text and encrypt the plain text with key 1. So let's go to our calculator. See if I can find it here. Okay, it is there. So let me copy the plain text, put it here. Okay, it's the same plain text, so no problem. And let me take the first key because I need to apply encryption with the first key. So I'm going to put the key here and I'm going to say encrypt. So this is the result. Let me copy the result. So what can we say? This is what? This what I just copied is what? It will be what? It will be encryption with K1, no? Of the plain text, give me that. Encryption with K1, isn't it? So I already did encryption with K1. Now I need to do this. So I need to take the result and decrypt it. So how do I do that? Using my calculator. So look at my calculator. It has an encrypt button and a decrypt button. So I should do what? What will be the input? The input will be this one, okay? So I take this one, which is encryption with K1 of the plain text, and I copy it here as an input. The key will be K2. So let me copy K2. And I'm going to put, oh, did I make any change? No. I'm going to put K2 here. And I'm going to say this time I have to decrypt. So I'm going to say decrypt, no? So this is the result. So the result will be this one. Now I need to do the whole. So what is missing to do the whole? I need to take that and encrypt it with K1, isn't it? So let me copy this. I'm going to put it as an entry here. I'm going to copy K1, put it as the key here, and say that I need to encrypt it. So the result is this one. So this is what they say. Verify that the result will be this one. So let me put it here and let's compare what they say. So they say that the result should be 4260, blah, 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 up to 7F, as you can see. Now, if I give you that, and I ask you to come back to that, you will be able, because you just have to apply this formula. So let me put the formula of decrypting. Let me put it here. Decrypting will be this way. So first, I need to go from here to here, isn't it? So look at, I'm going to take the ciphertext and I'm going to decrypt it with K1. So this is the ciphertext. I go here, I put it. And this is K1 already, and I'm going to decrypt it. Look at the result here. It has to be this one, AAC4A1. So we already did one of the 3 steps. Now, what should I do? The result, which is this guy, I need to encrypt it with K2. And when I encrypt it with K2, I have to come back to this one, to the B6 ECC, no? So I'm going to put it here. I'm going to put the key K2 here. And I'm going to say I need to decrypt it. I press decrypt, look at the result. The result is, I did it correctly? I have this AA, no, this one was not correct, no? The input have to be this one. So let me put it, the input was not correct. The input have to be this one, the key K2, and I need to encrypt it. So it's giving me B6 ECC, which is this one. And how I go to this one, to the clear text. So the formula say that I need to take the result here, and I need to decrypt it with key 1. So let me put the result here as an input. Let me put key 1 as an input. And I need to decrypt it. So I'm going to press decrypt, and this should be the clear text. So let's verify the clear text was 0A76 up to C36, as you can see, no? So I could come back. So there is another variation of triple dash, which is triple dash with 3 keys. So there is this the one that we just saw have 2 keys. So let me explain you triple dash with 3 keys. So the key, the resulting key will be 192 bits, which is 64 times 3. The effective key will be 56 times 3, which is 168 bits. So look at the key, which is 122 bits. You will break it in a first key of 64 bits, another key of 64 bits, and another key. So first, you take the plain text, you encrypt it with key 1. Then the result, you decrypt it with key 2. Then your result, you encrypt it with key 3. So you do that. So if I want to do the reverse operation, I walk this way. So if I want to come back to the plain text, what should I do? If I give you the ciphertext and I say, come back to the plain text, you first need to decrypt, because here you encrypt last time. So you first need to decrypt with key 3. Then you need to encrypt with key 2. Then you need to decrypt with key 1. So decrypt, encrypt, decrypt. So look at, here we have the decryption algorithm. We decrypt with key 3, we encrypt with key 2, and we decrypt with key 1, no? So we go the other way. Okay? Is it clear? So here you have an example. Let's say that the key is this one. So I should not have put a space here, I should have put all together. But because it's a 192 bits. But I break them, so you already know that this is key 1, key 2, key 3. I should not have done that. I make it easier for you. If you use this plain text and you use triple dash with 3 key, you should find this ciphertext. So you can apply it with the calculator that we have online to verify that it is true. Okay. Do you have any question about this? No? So let me show you. We have a lot of exercise on that. I need you to think about the exercise, not just to come here and to see me resolving the exercises. I need you to go over them and do them. So you will find, let me see, I think it's the exercise 3 that they start. We have exercise here on dash and triple dash. So I need you to start doing them. We are going to do them on Thursday. So review the algorithm, understand the algorithm, because otherwise this exercise are going to be difficult for you. So who do the algorithm? The mathematician do the algorithm for us. We program. And we just believe what the mathematicians say. Of course, because they are expert in the area, we are expert in programming. So we will see how to program this algorithm. You should be able to program it. But of course, I need you to understand the algorithm, because if you don't understand the algorithm, you are not going to understand the code that I'm going to write. So be sure you review this lecture before next class, no, in 2 days. Okay, thank you so much.